Okay, for this video, we're going to finish up talking about our colligative properties. So in the last video, we talked about vapor point depression, so we have 3 more to talk about here. So I'm going to start with freezing point depression. Now, what this means is that if you've got a pure solvent, so let's take some water. So let's say that's water. We know that water's freezing point is going to be about 0.0 degrees Celsius for pure water. If we add a non-volatile solute, so something that's not going to evaporate out of it, if we add a non-volatile solute, what happens, so we've got some solids, we're going to add them in, our solution is going to have a lower freezing point. And the amount lowered is going to be related to how much stuff we actually have in solution. The reason for, so that's what's going to happen. Now, how do I actually figure that out? Well, we want to know what's the change in temperature of our freezing point. It's going to be equal to the molality of the solution times something called Kf. As a side note, in case you've already done some reading, there is another term I. I'm not putting that in yet. I'm going to do all of these first, and then we're going to talk about what I means. There's a third term that you don't always have to deal with. So we'll wait till then. So right now I'm just saying it's molality times the freezing point depression constant. So what does this look like? How do we solve a problem like this? So let's take an example. So let's say we had a question like this. What is the freezing point if 0.200 moles of naphthalene, that should be an N, naphthalene, are added to 0.250 kilograms of ethanol. Now, for problems like this, either you have to be given the freezing point and the freezing point depression constant, or you have to look them up on a table. Like on a test, you might have a table of all these. You go find ethanol. What's true about ethanol? Well, when we look it up, for ethanol, we'll find that the freezing point depression constant is 1.99 degrees Celsius per molal, and that the freezing point for pure ethanol that doesn't have anything dissolved in it is negative 114.1 degrees Celsius, which is a way of saying this is usually going to be a liquid. You have to get it pretty cold to freeze, but we can make it even harder to freeze if we add some stuff to it. So now, what we calculate is the temperature change, the amount of depression, is equal to molality times Kf. So we need to find this molality term. So I'll do that over here to the side. Our molality, remember, is moles of solute per kilograms of solvent. In this problem, we already have it in the right units. Remember, colligative properties, it doesn't matter which particular substance is as long as it's non-volatile. So the fact there are 0.2 moles of naphthalene, we don't need to know its molar mass or its chemical formula even here. So it's a non-volatile substance. It's going to be 0.2 moles. And then it's moles per kilogram, and we're already in kilograms for ethanol. So this problem was purposely set up to be a one-step quick problem. Ooh, I dropped my calculator. So if we do that, we will get that our molality is, and I should have been able to do that in my head, 0.800 molal. So now we plug that in to see how much it's going to depreciate, how much it's going to be depressed. 0.800 molal times 1.99 degrees Celsius per molal. We multiply those out. We're going to get 1.59 degrees Celsius. This is amount it goes down. So that means our new freezing point is going to be equal to our negative 114.1 minus 1.59 degrees Celsius. So our new freezing point is going to be negative 115.7 degrees Celsius once we round. Depending on the source you look at, they'll deal with this negative in different way. You notice how the temperature went down? You will sometimes see versions where if you look up a freezing point depression constant, the constant is negative. And that's because it's saying, hey, it goes down. And so if you got a negative answer for this, well, then that's what I would add to the other values. Since I'm adding a negative, it's how much it goes down. What's important to recognize is that your pure solvent is going to be the highest freezing point, and when you add a non-volatile solute, it's always going to go down. So however you deal with the signs, just know however you calculate it, it should go down. And remember, going down can mean a number with a larger absolute value. Like here, we had negative 114.1. Negative 115.7 is smaller than negative 114.1. Since these are negative numbers, an absolute value number that's larger is something that is smaller. It's like being in more debt. So it is more negative. So the new freezing point is this. And that's all we're going to have to do with problems like this. Now, you also have something called boiling point, BP, elevation. It literally works the same way. It just has a different constant. And it's a different direction. It's going up, whereas freezing points go down. So our change in the boiling point temperature is going to be still our molality. It's going to be times Kb instead of Kf. They're different constants. So let's look for an example of that. So what we're going to do is we're going to ask, what is the boiling point, BP, of a 1.70 molal aqueous ethylene glycol solution? Now, this is a worded problem that if you had to look at a table does have a point that might be tricky to it. It's an aqueous solution. It's expected for you to know that means our solution solvent is water. So we need to look up the values for water. So we know that the boiling point for pure water is going to be 100.0 degrees Celsius. And if we look up the Kb for water, it's 0.512 degrees Celsius per molal. So now if we want to know how much the boiling point changes when we put enough ethylene glycol in this water solution to have 1.70 molal, well, that's going to be 1.70 molal times 0.512 degrees Celsius per molal, where those will cancel. And we're going to get it's going to be elevated by 0.870 degrees Celsius. So our new boiling point is going to be 100.0 plus 0.870 degrees Celsius, which we're going to round to 100.9 degrees Celsius. Since we're using this was only known to the tenths place, this was known to the thousandths, so we're rounding to that. And I covered me up. Sorry about that. I will get you. There we go. Sorry. For those of you following along very carefully, I'll give this a second. There's the whole problem. Both freezing point depressions and boiling point elevations are solved very similarly. The parts that can be tricky are usually making sure you know how to calculate the molality, or you might be given something like how much the boiling point changes, so you could find delta T and you might need to solve for the molality. Imagine you wanted to know, I want my water to boil at 101.5 degrees for whatever reason. Well, then I can plug it into this equation and solve for M, whereas here we solve for delta T. So if I wanted to be 101.5 and I was working with water, well, water boils at 100 naturally, so to get to 101.5, I need to elevate it by 1.5 degrees Celsius. And just because I've said that much, I might as well show what that would look like. So that would mean we would have 1.5 degrees Celsius equals molality times Kb, which was 0.512, because we're working with water here. So if we were to do that, we would get, we'd have to divide both sides by our 0.512 degrees Celsius, 0.512 degrees Celsius per molal. This would all cancel. And I would be given that I need my solution, if I want to raise it that much, to be 2.93 molal is what I would need. Now I need to know some more information about what substance I was working with, and then I could use that to figure out what concentration I needed to make. So that's the concentration, that's all it asked. It could also ask, you have so much water, how many moles do you add? So if you had a kilogram of water, you'd add 2.93 moles. So you'll just have to figure that out with the molality equation. So those two are really similar. The freezing point depression, boiling point elevation, you just have to remember, use different constants for them. They go in different directions. Freezing points go down, boiling points go up. Also, you might use the word like melting point instead of freezing point. They're the same point. So if a problem asks you about melting point, just ask you about the freezing point. It just used a different word because it's thinking of it coming from a different side. Are you going from solid to liquid or liquid to solid? But it's the exact same temperature. There's one final one that we've got to go over, and that is something called osmotic pressure. So what this is, at first this is going to sound like it's something that is highly specific, and you might wonder why in the world would this ever be useful? And then we'll talk about at least one fairly obvious application that when you go, I see why people study this. So the idea of osmotic pressure is, let's say I set up a YouTube like this and pretend like those are both the same size. I'm a bad artist. And initially, we were to put some water in both of them. And we had some solute on only the left side. So we started out with everything equal. This little thing here represents something called a semi-permeable membrane. Permeable. I can spell. What that means is that some substances can go through, but not others. In the case of where we're interested in osmosis, what it'll be is the solvent can go through, but the solute particles can't. So here, it would be like if whatever those solute particles were stuck on the left side, but the water was free to flow between them. Now, the issue right now is the left side is currently more concentrated than the right side. So what happens is, since the solute can't leave to equalize it, like if there was no barrier there, the solute would just over time migrate over to the other side, and there'd be equal solute on both sides. So if you remove the membrane, the solute just averages out. But since that can't happen, what instead happens, we're going to try to draw it again. I am not very good at these, but that's okay. Is this water level will rise, and this one will fall, effectively lowering the concentration of the solute. Now what you'll notice is there's a difference here, because gravity wouldn't want one side of the water to go up and one to go down, right? That would look weird. Like if you just look at some water, you would be like, wait, why is that one high and that one low? They should be at the same level. So that means we need a pressure, there's a pressure difference here related to how much that shift is. Just like when we talked about barometers, when we were dealing with our pressure measurements in 1211. Similar idea with our manometers. So there's a pressure difference there, and that pressure difference is called osmotic pressure. That's where the term comes from. I also want to point out that while we talk about it here, this looks like this really weird setup. You're like, okay, Dr. Leslie, chemists have tubes that they fill with these particles and have a semi-permeable membrane. When the heck does anybody do that? So there are other industry-related applications, but a big one is your body. Now, it doesn't look like a YouTube, but we deal with osmotic pressure a lot in biology because you have solute molecules, some of which want to be inside your cell, and some of which want to be outside your cell. And they're at different concentrations. And your cell membrane conveniently makes a semi-permeable membrane that some things can go across and some can't. So you'll talk about things where if you have solutions where your concentrations get off too much, you can, for example, make a cell swell up real big. Eventually, you can make it explode if you make the difference too much in concentration. Or you can make it in a solution where it shrivels up and all the water leaves the cell. Or you can end up in what's called an isotonic solution, where the water neither wants to leave or go in because it's just balanced just right between all the different ions. So when you get to hypertonic, hypotonic, and isotonic solutions, that's this osmotic pressure stuff just applied to biology. So there are actual applications that like real people worry about. It's not just crap we invent because we're like, well, we need to invent terms. So no, we don't do that. Well, I feel like it sometimes. I remember learning it as a student. There were definitely times where I'm like, there's nobody that uses that. But basically everything always seems like, oh, there is someone somewhere, and like a few someones that use any of these ideas, even the kind of more obscure ones. So that's our concept. Different, we've got solute on one side, none on the other, or maybe it's a lot of solute on one side and a little bit on the other, but it can't go through the middle. So to make the concentrations get closer, there becomes a difference in height. And as the difference in height grows, that's going to increase the osmotic pressure, so it's going to take more to be able to fight gravity, but it's also going to do that more if the concentration difference is larger. Because the larger concentration difference, there's a larger urge to, okay, we really want to try to get some water in there because it's way more concentrated on that side. Whereas if you, let's take the real extreme case, you put a single solute molecule in there, you're not even going to see the difference. Because it's like, well, technically there's a concentration difference, but it's so small that it doesn't apply enough osmotic. The osmotic pressure is so low that it's incalculable, so we don't see a height difference. Now the way we draw this equation is we use this symbol here. Looks like pi equals molarity times our universal gas constant, actually, times temperature. Now, in terms of units that we're going to work with, since we're working with pressure that's going to be in atmospheres, this R, we're going to use 0.0821 liters times atmospheres per mole Kelvin. So now that I've said a bunch, let's look at a problem, actually. Oh, right. I made this problem hard. I'm going to show you an easy version first. I'm just going to... Okay, as an aside, I'm making up a problem right now because I did this in class as well. The number might be unreasonable somewhere. As a heads up, we might get a pressure that's ridiculously high or ridiculously low because I'm just coming up with this. So let's say we had a solution. So let's say we made a glucose solution. So let's say we have a glucose solution. So we've got our solution. And it has a concentration of 0.500 molar. I don't think this will be too ridiculous. Let's say the temperature is 298 Kelvin. I'm going to go ahead and put it in Kelvin because you'll have to for the problem. And we want to know what's the osmotic pressure. So what's that? So we have osmotic pressure equals molarity times the gas constant times temperature. So this one is literally just plug these things in, right? Molarity, I'm going to write it as moles per liter to show you the units work out. Then R is 0.0821 liters times atmospheres per mole Kelvin. And then finally we have temperature, 298 Kelvin. So the Kelvins cancel, and then here moles are on top, moles are on bottom, liters are on top, liters are on bottom. Those cancel. So now we can do those, and this looks like it's probably a pretty reasonable answer. We're going to get that the osmotic pressure... Okay, that's a lot, actually. That's okay. We made a pretty concentrated solution. 12.23 atmospheres, or... we really have 3 sig figs, so 12.2 atmospheres. So that's a pretty high osmotic pressure right there. 12.2 atmospheres. Now what I wanted to show you is, so far, all 3 of our examples have been problems that are just, this is how you calculate it. In a lot of cases, though, there may be some application where you want to use this information to do something a little more complicated. So we're going to try this. The osmotic pressure of a solution containing 4.87 milligrams of an unknown protein. So a protein means it's probably going to be pretty big. Of an unknown protein in 10.0 milliliters of solution is 2.25 torr at 298 Kelvin. Again, we're not going to worry about determining the temperature change. I want you to find the molar mass. Now, in addition to the fact this is a whole bunch of words, if you pause me even and read it for a second, there's a decent chance, unless you've done one of these before, you might go, Dr. Leslie, what does the osmotic pressure have to do with the molar mass? This sounds like one of those things where you gave us a bunch of information but didn't show us how to do it. So let's think through our problem of what we can do and what we can know. So molar masses are related to both the mass of the protein and the moles. Did I forget? No, I didn't. So if we can find both of those values, we can find the molar mass. Well, they've told us the mass. That means I want to know the moles, right? We want to know how many moles are of this substance. So the question becomes, how are moles related to osmotic pressure? So let's look at our osmotic pressure. Osmotic pressure equals molarity times R times T. Well, molarity. That's got the word mole in it. It's moles per liter. And, oh right, we have a volume here. That means if I can find the molarity can go directly to moles from volume. We did that a bunch of 1211 and we practiced a bit earlier a couple videos ago. So if we can find the molarity, we can find the moles. And if we know the moles, and the problem told us the grams, we can find the molar mass. So we've got a few steps. Step 1, find molarity. Step 2, find moles. Step 3, find molar mass. Do some conversions in the middle of some of that. So let's find the molarity first. So our equation here, we want to get molarity by itself, so we're going to do osmotic pressure divided by RT equals the molarity. Now the osmotic pressure here is 2.25 torr. Wow, I write badly. Let's at least make that look like a 2 and not a 7. Let me read my problem. Yeah, the work I worked out was for 2.25. So first we need to convert that to atmospheres by dividing by 760. And so this is going to give us an osmotic pressure of 2.96 times 10 to the negative 3 atmospheres, or 0.00296. Then we divide. Our R is still 0.0821 liters times atmospheres per mole Kelvin. It's a constant, so it's not going to change here. And then we have a temperature of 298 Kelvin. If we check our units, the kelvins and the atmospheres cancel, And hey, liters or moles are part of molarity. And since it's liters and moles in the denominator, when you move it to the numerator, it'll flip up. So it'll become moles per liter. So the unit comes out like we'd expect. So we're going to take our 2.96 times 10 to the negative 3, divide it by 0.0821, and divide it by 298. And when we get this, we're going to get 1.2, make sure I'm rounding this right, 1 times 10 to the negative 4th molar. Well, now I need to convert my volume from milliliters into moles. So we're going to start, and you could write the molarity equation out as one way to solve this. I like always doing these as conversions. So I'm going to write my 10.0 milliliters, and I know that every 1,000 milliliters is 1 liter. And I know that for every 1 liter, this is going to have 1.21 times 10 to the negative 4th moles. So if I were to do that math out, I'll get 1.21 times 10 to the negative 6th moles. So that's our moles. So finally, we want molar mass. Molar mass is grams per mole. So we have milligrams, so I have to start by dividing that by 1,000, and that'll get me 4.87 times 10 to the negative 3 grams, divided by 1.21 times 10 to the negative 6 moles. And from there, we will get 4,020 grams per mole. A pretty large molar mass, but that makes sense. It's a protein. Proteins have lots and lots of atoms, so that's good. And sorry about that. There you go. I said 14,020 out loud. I know this video is kind of long, but I only have one last thing to do, and making an entire video for this doesn't seem worth it. Like, I think it'd be weird to have a 4-minute video after this, so we're going to do one last thing.